say we get a solution where we can't easily take the inverse, right? How do you actually implement this in Matlab or a tool where you can do a numerical inversion? Okay, so there's this function. Let's just write it out here. So there's a function called Talbot Inversion. So the function looks something like this. It's t is equal to this function Talbot underscore inversion. Okay, Talbot inversion, and that takes the function. So it's a function in the S domain. Whatever the function in the S domain, that's something you write, or you're going to write a function like we just went through and came up with this function here based on our problem. That's our function in the S domain. So we'd write a MATLAB function that evaluates that at t hat of S. We'll pass that to Talbot inversion. And then we also need to pass to it a vector of time. Vector of time or times. Actually, it could just be a single time, but you would pass it a vector of time, and then what it's going to return is a vector of temperature equal to the dimension of the vector of times. That's the temperature at each time that you're trying to evaluate. Right, so think about that. We have our function in S. We don't even bother inverting it. We just put it in MATLAB and let MATLAB in this sort of it's a really kind of elegant function. I'll show you in a second, but we let that do the hard work of doing the inversion for us, and we get back our solution. So let's actually look at how this would be implemented in MATLAB. All right, so here, this Talbot inversion function is not something that comes with MATLAB. It's something you have to download. You can download it from the homework folder, I believe. It's also in the lecture folder for today, the same file. But it was written by, I think, a third party, and then MATLAB decided to publish it as well. So this Talbot inversion, what it's doing here is it's taking your function, some function of S, and I'll show you how to call that in a second, and then it asks for a time or vector of times to go with it. And then if you scroll down, you can see this is actually the entire function right here. Okay, this is the entire function of doing the inverse is this, and I've looked at it a little bit. I can't actually figure out what it's doing. It's kind of amazing, but you're doing this entire inverse in basically 3 or 4 lines of code, right? Which is really incredible given the amount of people who have been slamming their head against the wall to do inversion for centuries, right? So this is the function. All you have to do is pass it. So let's look at the example. So here we write our own function t hat, right? This is our evaluation of t hat as a function of S. So we're going to take in to this function different values of S, and then some things that we need to evaluate it. Right? These are just arguments that go with whatever the definition is. We have t infinity, our generation, some other constants. Okay, then we're going to go through and we're going to calculate for each S that's passed to us a value of t hat. So we do this with a loop. So let's say we have n values in our S vector. We just loop through all those n values and calculate each of the t hats. And then we pass this whole function to the Talbot inversion. Incidentally, we're doing this with a loop here, but another way of doing it is just with the dot operator. So if you use MATLAB, this is a really handy way of dealing with repeating the same operation on a whole bunch of different elements. Okay, so this dot operator is just saying every time I have an element in a vector, I'm going to do the exact same thing to every element. So if it's dot divide, I'm going to divide all elements by that thing individually, dot multiply, so on. Right? So that's these two things, this here and this loop, are equivalent. Right? But they're both there. Okay, so then to run this, we set up our script. We're going to specify the constants. Come down here, and then I'm going to create a vector of time. One thing you might want to make a note of is Talbot inversion sometimes doesn't do very well at 0, at time equals 0. So you may want to start at something just a little bit bigger than 0. So for this problem, we're looking at 0.01 seconds to 10 seconds and 101 time steps. Okay, this was the analytical solution just for reference. We'll plot that here. And then I'm going to compute, using Talbot inversion, my Laplace function here. So I'm passing to that S. S is actually let's see, S is actually defined by the function itself. So I don't anywhere in this code, I'm not saying here's a vector of S. I let the Talbot inversion function manage that. Okay, but I just need a function that takes in S and then all the other stuff that I need to evaluate it. And then you give it this vector of time where you want to evaluate. Right, so the function itself only requires S, so we're going to use this mapping to map it from our arguments down to a single argument. Okay. So if we run this, we should see that the Talbot inversion matches the analytical solution. Here it is. Okay, so our blue dots are pretty much perfectly over our black line, which is the analytical solution. Okay. Any questions on this? All right, so for the homework, let's do, well, now, next Friday, you're gonna need to use Talbot inversion. All right, so you should maybe make sure you understand what we're talking about here, but what you're gonna do is you're gonna derive this solution. You really can't have there's no solution for the homework problem that you could have that could be inverted unless you have some really detailed table somewhere that I don't have, but there's really no way to invert it. So the numerical inversion is the only way to do it, and you'll use Talbot for that. Yeah. I think there's a paper that goes with it. In fact, in the comments, so like a journal paper that goes with it. So if you look here, yeah, so you could look at this paper if you really were, but like this is the kind of thing that's, it's a few lines of code, but it very easily could have been somebody's master's thesis, right? Right, they go through and probably have some proof that it is a rigorous proof that it works, and in the end they have this contribution, but it's yeah. So there's probably some thesis or in addition to this paper that goes with it, but that's basically all I have for it.